Welcome to Geometric Models. We want to solve a system like this. And in order to get this a bit more concise, this notation, we'll write everything as vectors and matrices. So the solution vector that we want to have is x, x1 to xn inside the Euclidean space R to the n, and we can write these coefficients of these equations all into one matrix Aij in R to the m times n. We have m rows and n columns, and then the equation is just Ax equals b, where b is the right hand side, is of the form b1 to b, let's see, m in R to the m. We are interested in the case that we have more columns than rows or the same size, same numbers of these. So m less than or equal to n. This case is of interest here. The other case is when it's overdetermined. That'll come in some other lectures. For example, let's look at this equation. x1 plus 2x2 equals 1, and 2x1 plus x2 minus x3 equals 0. Here's the case. We have three variables and two equations. We have the coefficient matrix A, write them out. 1, 2, 0, 1, 2, 0, 2, 1, minus 1, 2, 1, minus 1. The right hand side B is the vector 1, 0, and well, the solution will come to that. This is just our example that we're looking at, and now we're going to say something about two different kinds of right hand sides. Namely, the homogeneous case is when the right hand side is 0. Homogeneous case. B equals 0. So we have the equation Ax equals 0, and we want to solve this. Okay, what do you do? Well, you do operations, row operations. And this amounts to bringing up the coefficient matrix A into an equivalent form, upper triangle form. So take to upper triangle form. That means you want to find matrix C in n times n, a square matrix which is invertible. It represents the row operations that you do on the coefficient matrix. And then C times A is a staircase form of this kind. You could also call it full staircase form. So you might start here with a 1, you don't have to, but 1, I mean, if it's non-zero, then you can make it into a 1. Then say you have a staircase here, and then perhaps here not. And the next step is here, and perhaps here, and then like this, for example. And above all those entries, you have something indicated by a star. As an example, full staircase. That's enough. You can use that in order to solve your equation Ax equals B. How do you get this operation, this matrix C? Well, you look at the individual row operations that you do. In each step it has to be invertible. And then you get an invertible matrix C. Invertible row operations. What do we have? you can add a row onto a different row. Say add alpha times row I onto row, multiply row I with some alpha, some beta non-equal to 0. And what else can you do? You can swap two rows. Swap rows I and j. And these come up with special matrices which represent these operations. These matrices will be multiplied from the left onto A in order to get that. We'll come to this. But first of all, let's check that these are invertible operations. And they are by specifying their inverse operations. So inverse operations. The first one, well, you have this jth row which has been changed. You change it back with the same ith row, but multiply it with minus alpha and add it onto that, and you get back what you had before. So add minus alpha times ith row onto row number j. Second operation can be inverted by multiplying the ith row with the inverse of beta. Multiply row I with beta inverse. And that's why we needed beta non-zero. And the swapping, you interchanged I and j. Rows I and j will be, well, you undo this by interchanging them again. Swap rows I and j. And now the thing is, these can be, I said you can express these operations by matrix multiplication from the left. Let's do that. One can also fully write down as a general matrix, but you'll see how it works in the example. So we want to multiply our A. A is the matrix that was 1, 2, 0, 1, 2, 0, and 2, 1, minus 1, 2, 1, minus 1. So which operation would make sense? You could multiply the minus 2-fold of the first row onto the second row. In order to eliminate this 2 here, get a 0. So multiply from left. Which matrix? Such that this happens here. The first row multiplied by minus 2 gets added onto the second row. Let's try this matrix. 1, 0, minus 2, 1 times A. And let's see. Let's multiply this matrix here with this matrix A. You take first row of this one and multiply it with every column. It just picks out the first column. Nothing else happens. And the second row here multiplied, well, it'll multiply the first, every element of the first row with minus 2 and add it with an element in the corresponding place of the second row and write it into the second row here. That's exactly what we wanted. Minus 3 and minus 1. Right? And the next one is what we want to do. We want to multiply here this with minus 1/3. Minus 1/3. This will be this matrix. 1 minus 1/3. 0, 0. So it's going to just be a diagonal matrix. And I claim you take the second diagonal element, and that entry is the multiplier that you want to have here. Let's check. 1, 0, yeah, it just picks up first row. And the second one doesn't pick anything here, but from the second row. So that will be 0, 1, 1/3. And then we have the staircase normal form in the full staircase normal form. There are other staircase normal forms, but here this is sufficient for what we want to do. Full staircase normal form. Assume you have the full staircase normal form for your system of linear equations, and then you want to get the solution from that. So obtain solution from your full staircase form T. In our example, I'll just do it with this example here. It was the matrix 1, 2, 0, 1, 2, 0, 0, 1 minus a third. How do you get the solution? Well, how would you naively do it? We'll just write it out down as equation, then we can see what's happening. So equations x1 plus 2x2 equals 0, and the other one is x2 minus a third times x3 equals 0, and it's not square, right? There's some equations missing which are not encoded in this staircase normal form, but it is, you have a parameter, a free parameter for x3. We'll call this s. How do you solve this equation? You see, this equation has one unknown, x3 is something, it's a parameter. And then upstairs, you have an equation with two unknowns. x3 is there and a different unknown, x2. And then you got one more. You have the x2, and well, you might have some x3 in it, but these are all known. Okay, here's no value for no coefficient for x3, but there could be one. And the only unknown here is x1, because you know this one here from that equation. And if there were a coefficient here with x3, you would know it from here, from there. So this is called backward substitution. So how you do that? You take this one and plug it in here and solve. And then you take this and plug it in here and solve, and so on. Go up all the way, all the steps backwards up. Okay, and in this case here, now let's solve it. We can write down the solution vector x1, x2, x3 equals s times, okay, here x2 equals minus a third x3, so 2 equals a third times s. Here's the 1, a third. And then plug this in. I'll write it out here. Equation number 1, x1 plus 2, but 2 is times x2. x2 is a third s, 2/3 s equals 0. So you have minus 2/3 s, and the s is taken out here. And s can be any real number. So your solution space is a one-dimensional line, a straight line. It is a one-dimensional sub-vector space of R3, or a linear subspace. In general, this is the structure of your solution space to a system of linear equations. Homogeneous case. It will be a linear subspace. What does that mean? It means if, in general, if x and y in R to the n solve ax equals 0, then the sum x plus y will also be a solution. Let's check. A times x plus y. What are the rules for multiplying matrices and vectors? Okay, you have the sum here, distributive law, ax plus ay. This is 0, and this is 0, because x and y are both solutions, so you get 0 plus 0 equals 0. Fine. Next, if x in R to the n solves ax equals 0, and you take alpha a real number, then alpha x also solves. Plug it in. A times alpha x, alpha times ax, but this is 0, then you get alpha times 0 equals 0. So the additive property and the scaling property of the solution set means that the solution space is a linear subspace.